Okay, so good evening. Good evening, everyone. My name is Devarun Banerjee. I am going to conduct a live interaction session based on this particular NPTEL course, Physical and Electrochemical Characterizations in Chemical Engineering. This is live session number 2, and it's been conducted on 5th February 2024. I am a PhD PMRF scholar from Indian Institute of Technology, Delhi. So in this week, in the first lecture, what was covered was the fundamentals of infrared spectroscopy. So basically, what happens is, uh, so what do you do by the infrared spectroscopy? We try to measure, we try to measure the varieties of the energy difference of a particular molecule. So a molecule in space consists of varieties of energies. Includes rotational energy, vibrational energy, electronic energy, like that. Among them, vibrational energy is basically what is been uh, measured via the infrared spectroscopy. So rotational energy is basically happens as a result of the body's rotation around its gravitational center. Vibrational energy happens as a result of its atomic periodic displacement from the points of equilibrium, and electronic energy is generated when the electrons are connected with each atom. Okay, so when we talk about the variety of the electromagnetic spectrum or varieties of electromagnetic radiation, it basically depends upon the wavelength of frequency. So wavelength is basically the inverse of the frequency. So in this direction, the wavelength is increasing in the electromagnetic spectrum and the frequency is decreasing. So from X-ray having a lower wavelength, highest frequency, from that UV visible, and then the infrared, which is the point of interest, region of interest in our case, in this case. So if we further classify the infrared region, it happens to be a near infrared, which happens to be at 400 to 10 centimeter inverse of wave number. Wave number is again similar to frequency, it's the inverse of the wavelength, and that's why it's expressed in terms of the centimeter inverse. Like so, near infrared region where low energy is having, then the middle infrared, and then the far infrared, which is having a the highest of the basically the wave number, means the highest of the frequency. Okay. So what is the basically infrared spectroscopy? Infrared spectroscopy is that infrared light excites the molecules to a particular higher vibrational energy state. We give the infrared energy input to the molecules, to the particles, it gets excited, and its vibrational energy gets changed. Okay. So basically the what amount of light, because of the amount of light absorbed, infrared light absorbed, the this particular absorption is basically quantified, and that is we get in the terms of the particular infrared spectra. So infrared radiation absorption results in energy shifts between 8 to 40 kilojoule per mole. The absorption of infrared light increases the amplitude of the vibrational movements of the bonds in the molecule. As I told, that because of the absorption of the infrared light, the vibrational energy gets changed of the particular molecule, and that is why they get uh, basically excited, and that is why how much amount of that particular vibrational energy is getting changed, that is measured by this particular spectroscopic technique. Okay, so The question is that every bond, each and every molecular bond in nature, uh, so will it be particularly infrared sensitive? The answer is no. Not all molecular bonds can absorb infrared energy, even if the radiation frequency precisely matches the bond motion. So, which bonds would you know? The bonds having a changing dipole moment may absorb infrared light, which means that if there is a particular electronic energy difference between the two molecules, if it's a diatomic, or between the overall in the molecule, if it's polyatomic, so such as HCl. So Cl is much more electronegative. So there is basically a dipole moment in the particular molecule. H is having a delta plus and Cl is having a delta minus. So because of the infrared absorption, this particular HCl molecule will be showing a difference on the of the dipole moment, right? And because of that, there will be a particular spectra we'll be having. On the other hand, if we get a symmetric molecule like hydrogen, H2, so there is both are the HH. So both are having a similar dipole moment. There is a net. There is no kind of uh, delta plus or delta minus. So obviously there would be a bond stretch or bond difference, vibrational difference, but it would be the negated, or it would be kind of cancelled out because of the similar kind of nature of the particular two atoms. So uh, the shifting of the electrical dipole of the connection may then pair with the incoming radiations sinusoidally changing electromagnetic field. Okay. Each molecule has a unique infrared absorption pattern or in or infrared. Each kind of bond has its own inherent frequency of vibration. You need to understand. So continuing with this, each kind of bonds absorption, such as NH, CH, OH. So this having a different, there is a certain net dipole moment is having in this particular in these kind of bonds, CO, C double bond or C single bond. Uh, so, however, there these particular bonds, the examples are shown here, is having a consisted in a very tiny part of the vibrational infrared area. Okay, so it's a very difficult also to measure this kind of thing, this kind of bonds via normal infrared spectroscopy. So, for example, the absorption in the range of 3000 to 2850 centimeter inverse range is usually always due to the presence of alkyl CH bond in the molecule. Uh, the CO bond, the carbonyl bond, shows about 1780 to 1710 centimeter inverse of the wave number range. Okay, so these are the kind of those fingerprint areas of this particular functional group. So the vibrational energy changes. Some of those modes. What are the some of the modes? The bonds can be stretched. If there is a particular bond, it can be stretched, like it's shown here. So there can be a bending vibration. Bending vibration might be of two types: in plane or out of plane. In plane means if it considered it as a 3D, then towards the inside the particular page. So the entire bond is actually getting moved into the page. If it's of X, Y, Z three directions, right? Or out of the plane means this is coming out of this particular this uh, PC window, like that. So bending vibration is different from the stretching vibrations. Bending vibrations alter the angles of bonds but do not extend them. It does not stretch it, but it angles it changes. Okay. The frequency of vibration changes according to the kind of vibration. The frequency drops as the number of bonds increases. Further types, if we see the examples like the scissoring. Uh, Again, this is this kind of the examples are also shown here. Uh, this kind of bond bending vibrations are there. These are all types of bending vibrations. Okay, scissoring, wagging, rocking, twisting. So rocking is particular in plane. So it's basically a 2D. It's very difficult to show it in this particular manner. So this is in plane, but both will be the similar direction. It will be talk as a rocking. A twisting, both will be the out of plane in the similar direction. There will be a twisting, and then also the normal bending vibration like the scissoring or wagging are there. So stretching vibrations have the variations like symmetric stretch or asymmetric stretch. So in the same direction it is happening. It's called the symmetric stretch. It comes and thus for the CH bond, if it's a symmetric stretch, it comes at around 3000 centimeter inverse wave number. For the CH bond, if it's a asymmetric stretch, then it comes around a 3200 centimeter inverse. So by these particular fingerprint things, we identify whether it's a particular uh, kind of bond is actually present. Similarly, further examples are also shown here for some other functional groups like the methyl group, amino group, anhydride group, nitro group, like that. If it's a asymmetric stretch or if it's a symmetric stretch. Okay. Then we go for the polyatomic molecules. Till now we're talking about the diatomic molecules. Now we'll be talking about the polyatomic molecules. Okay. So for the polyatomic molecules, the basically the vibrations of the polyatomic molecules are more complex. So here obviously more than two atoms are there. So a molecule with three atoms and two bonds has four vibrational modes. How there is four vibrational modes? Like if it can have a symmetric stretch at the same direction, stretching vibration. It can have a asymmetric stretch in different directions, or it can have two types of bending vibrations. So this kind of the both oxygen have, like the out of plane or the inwards plane. So this kind of four uh, vibrational modes can be seen here. So this one example is shown here for the CO2 molecule. Okay. So CO2 is as a linear molecule. So we see here for a non-linear triatomic molecule such as water, H2O. So again for H2O, there are again multiple types of vibrational modes. So it can have a asymmetric stretch, like can have a multiple way of the stretching. It can have a basically symmetric stretch. It can have a symmetric bend also, right? So this kind of multiple types of the stretching and bending vibration can happen. With this, we come to the first question today. The IR spectra refers to which energy transition of a molecule? Rotational, vibrational, nuclear transition, or bond breaking?
Vibrational. It's a vibrational one. Hello, can you hear me, sir? It's a B vibrational one.
Yeah, yeah. So you're right. Mhm. So it's the vibrational energy is the basic already told. So the next question is the wave numbers are calculated through the uh, wavelength dash of the wavelength given in centimeters. Square, cube, reciprocal, or square root.
It's a C, reciprocal of wavelength.
Yeah. So it's the reciprocal of wavelength. It's centimeter inverse. So the wave numbers are basically the one by wavelength, which that is why it's given in the centimeter inverse. So here's a simple numerical problem. So the force constant for CC double bond is given as 10 into 10 to the power 5. Take it as 10 to the power 5. So dynes per centimeter. The stretching frequency is given in centimeter inverse of the same will be approximately what it will be. The speed of light is given as 3 into 10 to the power 8 meter per second.
Sorry, sir, no idea.
Sorry.
No idea.
Okay. Okay. Uh,
I think we have to
so
use the half K into del V squared. We have to use that.
I think there is some noise coming from your side. So whatever you want to say, you can use the chat box. So basically, uh, mhm, the wave number is given basically by this particular formula. It's wave number equals to 4.12 multiplied by square root of k by nu, where k is the force constant, nu is the reduced mass. So the force constant is for this particular bond is given is 10 into 10 to the power 5 dynes per centimeter. Nu is the reduced mass. What do you mean by reduced mass? It comes in by this particular formula. So whatever the molecule is found by the by the atoms, so you have to calculate the reduced mass or the apparent mass of this particular molecule. So it comes by this particular formula. M1 M2 divided by M1 plus M2. So carbon having a, atomic weight of molecular weight of 12. So 12, both will be 12 because it's CC double bond. So by this it comes the reduced mass as 6. Okay, force constant is given. Just put the values and you'll get about 1682 centimeter inverse. Is the basically the theoretical value of this CC double bond uh, stretching frequency. Which of the following bending vibration takes place in different planes? Asymmetric stretching, rocking, scissoring, twisting.
I think so. A, asymmetric stretching.
No, see, so it's the question is told about its bending vibration. So obviously the stretching will not be the answer. So it might be the other options. So asymmetric stretching is a stretching vibration. It's so the length of the bond gets changed, not the angle. So the bond doesn't get bent, rather it gets stretched. Okay. So the different types which were shown earlier, like scissoring, wagging, rocking, twisting. Okay, these are all the types of bending vibrations. Among them, twisting is particularly uh, called when the bending it takes place in different planes of the out of the plane. Okay, so it is called the twisting. For the bonds, CC, CBr, CO, CCl. So these are all the different types of carbon single bond. So the highest and lowest stretching frequency would be from uh, C. So these are the options: CC and CCl, CBr and CO, CC and CBr, CCl and CO. So for the bonds, the carbon single bonds, CC, CBr, CO, CCl, the highest and lowest stretching frequency shall be from, and these are the options.
Maybe B answer. Answer maybe B, sir.
No,
Oh,
so see, basically what happens is the so the one of the atom of this particular diatomic molecule is fixed, is the carbon. So it will be depending upon the mass of the this particular the other atom. So if you see the earlier formula which I discussed, that wave number is basically inversely proportional to the mu. Mu comes with the mass of this particular molecule. So with the mass increasing, the vibrational frequency will be decreasing. So basically, it having an inverse proportional relationship. So accordingly, among these particular options, CC will be having the highest one, and the CBr, the bromine one, be having the lowest one among these particular options. And if we see the other options, so basically CH, because of hydrogen is the lightest mhm, atom, so CH having the highest wave number, and CI among these particular like halogen atoms, CI bond will be the lowest one. Okay. So as the mass of the atom bound to carbon rises, the decreased mass increases and the vibrational frequency drops. So and the wave numbers gets smaller and smaller. So when we're talking about these particular stretching vibrational frequencies, let us also check some further points. So K is particularly it's called this particular is a variable constant which changes according to the kind of the bond. So it will be depending upon the kind of the bond, and that is why this particular value needs to be also identified. Okay. The triple bonds having three times the force constant, the K values compared to the single bonds, where double bonds have the twice the force constant. Okay. So what will basically happens is the higher force constant of a particular bond, it means that the this particular stretching vibrational frequency will be higher. Because it's simple this particular formula you see that wave number is directly proportional to the square root of the force constant. So higher the force constant, higher will be the frequency. Bonds between a heavier atoms vibrate at a lower frequency. Already discussed this thing. Triple bonds between the same two atoms are often stronger than double or single bonds and have higher vibrational frequencies. So that is already told that triple bonds is having a much higher force constant, and that is why it is actually often considered that stronger than double or single bonds and have that is why higher vibrational frequencies. Also hybridization having a immense effect on the particular force constant. So if you see basically it nothing but this kind of bonds, right? So sp hybridization of carbon, it means that is a having a triple bond, and the same thing the uh, frequency would be higher for a triple bond. So in one way or the other, you can say that hybridization also has an effect on the particular force constant. So for carbon hydrogen bond vibration, it goes like that the this particular bond strength like sp2 sp3 like that, and it goes along in this way the vibrational frequency gets decreased. Additionally, the resonance has also an effect on the strength and duration of the bond, okay, as well as on the force constant. So for example, the CC double bond, there is a particular CC double bond, and it can see that there is a particular aldehyde group or ketonic group is actually attached to it. So this particular CC double bond absorbs at a lower frequency at about 1675 to 1680 centimeter inverse, which is less than a standard ketone absorbing at 1715 centimeter inverse. Okay, so compared to the standard ketone vibrational frequency, CC double bond. So because of this particular presence of this particular CO double bond and because of the lone pair of the oxygen, so this particular CO bond it behaves like a single bond. So due to this particular resonance between the CO, the distance between C and O gets increased and it behaves like a single bond. And as we know that the single bond having a lower vibrational frequency compared to a double bond, and that is why what happens is that particular it affects the particular CC double bond. So it its frequency gets lowered compared to the uh, what is the for a standard ketone. Okay. So the lecture 2, it covers about its continuation basically of the particular lecture 1. Further covers the infrared spectroscopy, the IR bands and its applications. Okay, so we are now slowly moving into towards the application thing also, like the FTIR and those kind of things. So what is a basically infrared activity? So only a subset of the entire number of the normal vibrational modes in a particular molecule is detectable via infrared spectroscopy. These type of vibration are referred to be infrared active. So as I already told that each and every vibration, each and every molecule will not be infrared active. There has to be a certain change in the dipole moment. So molecular dipole moment alteration is required to be infrared active. So that is why we don't get the infrared, like if we give a pure copper metal, so we'll not get any kind of infrared spectra of it, because it's a very symmetric kind of thing. There is obviously there is a vibrational energy change when you give the infrared uh, light input, but there is no change in the net dipole moment, because everywhere there is only copper, 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 like that. So if there is certain net dipole is there, so due to the change of the particular stress bond energy, due to whatever stretching or bending or other modes, so due to these reasons, there is also change in the dipole. So we uh, indirectly measure that particular change of the energy via the particular because of the dipole moment alteration. Okay. So the radiation's oscillating electric field interacts with the molecule and it induces molecular dipole moment. That is why the dipole moment alteration is created, and we measure this particular, there is a particular vibrational frequency we measure. So infrared activity requires that the rate of change of the dipole moment with vibration is zero, non-zero, positive, negative. Infrared activity requires that the rate of change of the dipole moment with vibration is zero, non-zero, positive or negative.
Maybe the answer is C, positive.
So it needs not to be a directly, it can say that it needs to be a positive. It basically needs to be non-zero. So basically the infrared activity requires that the rate of change on the dipole moment with respect to the vibrational mode be non-zero. So del nu del q should not be equals to zero with respect to the vibrational mode change. Nu is this particular rate of change of the dipole moment. Telling. Okay. So when basically what is the dipole moment is that when two charge centers in a molecule are separated by a distance, a certain distance, there's a particular distance between the two at two atoms in a particular molecule is defined as L, and E is the amount of electrical charge. So mu is the dipole moment. So mu equals to the amount of electrical charge multiplied by the inter atomic distance. So with respect to the rate of change of the dipole, with respect to the vibrational mode, the rate of change of the dipole moment should not be equals to zero. So the with this already told that the HCl molecule possesses a permanent dipole with an infrared active stretching vibration due to the change in dipole moment during stretching vibration. So because of the H and Cl, there is electronegativity difference. There is a permanent dipole moment. There is permanent dipole. So that is why due to the infrared um, uh, absorption happens, this particular L gets changed. So because of the difference in the charge, there is a certain delta plus is on the H and delta minus is on the Cl. So there is the dipole moment alteration. On the other hand, the H2 is particularly a symmetric molecule. So whatever happens, whatever change happens on the H, the same thing happens on the this H also. So basically it gets cancelled out. So ultimately there is no change of the particular dipole moment, and due to that the dipole moment is always zero during oscillation of this particular hydrogen. It is infrared inactive. So similarly, the CO2 having a center of symmetry, and it actually at equilibrium it possesses zero dipole moment. So for CO2 there are multiple kind of stretching or bending all can happen already told. So the symmetric stretching is be infrared inactive. So the same thing will be happening because CO2, the C is the center, the two oxygen atoms are in the two sides. So if it's a symmetric stretching, again it will be get cancelled out. So both two electronegative atoms are on the two sides of the electropositive carbon. So basically the net dipole moment change will be zero. Basically with respect to the frequency change. So the symmetric stretching is actually considered as infrared inactive. But if it's a asymmetric stretching, so the L, if it we consider this particular this distance between the CO, the two CO bonds L1 and L2. So if L1, the delta L1 and delta L2 is not equal, then there will be a particular change in the uh, alteration in the dipole moment. There will be net change in the dipole moment, and that is why the asymmetric stretching is considered as higher active. And similarly, bending vibration actually also induces a non-zero dipole moment. Okay, and thus it's also uh, infrared active when it's a basically bending. So there is a bond angle change instead of the stretching. So whenever there is a particular bond angle change, there will be always a net dipole moment alteration. The species characterized by polar bonding like CO, NO, OH, they have prominent infrared bands due to the same reason, whereas the covalent or the non-polar bonds such as CC single bond, CC double bond, NN double bond, H2N2, just absorb IR in a weak or in a non-existent manner. No, same things are again getting repeated. So the vibrations in groups are vibrations of a tiny set of atoms that are much more energetic than the rest. Okay, so the group vibration frequencies are nearly completely independent of the molecule's structure. They are often located far above or below the skeletal mode. Several instances include the vibrations of light atoms in terminal groups, like CH3, OH, CN, or C double bond O. So there are the kind of different instances where the vibrations of light atoms in terminal groups. Okay, there will be a certain dipole moment change, and that is why we get uh, infrared activity. Heavy atoms, CCl, CBr, metal, they vibrate at a low frequencies. Already told there is a kind of a inverse proportional relationship with the nu bar and uh, the reduced mass. A bigger molecule will almost certainly have a high number of vibrations. Normal vibrations are divided into two categories: skeletal and group vibrations. Okay, very told here. Uh, all atoms experience the same displacement during this kind of vibrations. And an example is shown here, like for a normal carbon chain length of an organic molecule, it vibrates at the range of the 1400 to 1700 centimeter inverse. So the vibrational frequencies of metal adsorbate region usually lies in the region of 4000 to 200 500 centimeter inverse, 450 to 200, 2000 to 1500, or 1500 to 500 centimeter inverse. These are all given in the terms of wave number.
Maybe C 2000 to 1500.
So see, the metal adsorbate, it means that it's having a very low wave number, right? So basically the correct answer is actually this fingerprint happens and a very low wave number range. It's the 450 to 200 centimeter inverse, where the 4000 to 200 500 this centimeter in this particular range is for the XH stretch region, uh, and the 2000 to 1500 is actually happens for the normal double bonds. So C double bond O, C double bond C, this kind of. And for the triple bond is slightly higher, so it's to 2500 to 2000. So if we want to analyze this particular band intensities, so the band intensities are estimated using a few basic criteria. So the polar bonding provide very bright infrared peaks. Polar or non-polar bonding with low peak intensity result in the formation of weak infrared bands. So a simple thumb rule is basically the intensity of a molecule rises as the number of similar structural components increases. So more and more this particular bonds will be there. There will be the intensity of a particular spectra or the particular peak would be increasing. So this particular thumb rule is interesting, that we already seen that del nu del q should not be equals to 0. So keeping in mind this particular criteria, the intensity of an infrared absorption band is related to the square of the dipole moment chain associated with its vibration. So intensity is directly proportional to the del nu del q whole square. So this is one of the kind of a fingerprint or like a thumb rule kind of thing. Not sure how much it exactly it can be used to quantify, because usually FTIR or like this kind of IR techniques is not for the directly quantification things. So not only does the infrared energy beam travel through the material under examination, but it also travels through a length of air, and due to which what happens is a certain background spectra also comes. So in the air, what the two most abundant infrared active substances are carbon dioxide and water vapor, right? So nitrogen is also there in air, 79% like that, but nitrogen or oxygen, they are infrared not very much active, so they does not make any problem. But CO2 and water vapor, H2O, they is to having a particular bending vibrations. So the bending vibrations we see, so similar to the CO2 also, the bending vibrations. So they are the infrared active substances and they give a certain peak. So what happens is usually a blank run is usually taken and that particular data is actually stored in the particular our instrument memory. So when you then use a particular sample IR spectroscopy, so removes that particular air or the air spectra or the background spectra from it. Otherwise, we will be very much confused that this particular the vibrational frequency peak is coming from our sample or it is just this noise because of the air. So after determining the spectrum of the sample, the computer subtracts the background spectrum from it, thus eliminating the air peaks. And in this regard, there is a particular example of mesitylene and 2-pyrrolidine are shown here, where this particular black one is of the air. You can see there is a certain small peaks are also there, not very prominent, but also not very uh, small to be ignored. So you can see here. So there are two kind of spectrum. If it's a transmittance spectrum, so the vibrational band peaks point downward. If it's a absorbance spectrum, the peaks pointing upwards. So the vibrational band modes are changed in these two types of spectrum: the transmittance spectrum and the absorbance spectrum. What are the some limitations? So some of the characteristic bands may overlap with each other with this particular infrared spectroscopic technique. So, for example, the atoms such as oxygen and nitrogen connected with hydrogen, so NH, OH, this kind of bonds, they show the frequencies in the similar region of spectrum. However, there are certain elements which can remove the characteristic bands in molecules. So there are certain elements. So what happens is when we trying to quantify that particular NH bond or the OH bond, so it will be also be connected with some other element also. So if we can get the characteristic spectra peak of that particular bond, we can get the presence of whether the nitrogen is also there or not. Otherwise, it becomes difficult with to identify whether this if it's an NH or it's OH, or maybe N is also connected to some other element also. Then from that we can say that okay, now we are sure that nitrogen is present in our sample, not the oxygen. So now we are sure that it is not a OH bond, it is a NH bond. Like that you can say. So the characteristic bands become less distinct when there is a strong vibrational coupling due to slight variation in atomic masses and bond strength. Okay. So, a simple problem. What is the absorbance of an IR peak with a 25% transmittance? I've already told that there are two modes basically of this particular infrared spectroscopy. It's a absorbance or it's based on the transmittance. So if it's having a 25% transmittance, so what would be the absorbance? It's 0.6, 0.81, 2.5, 1.04. So there is a basically formula between the absorbance and the transmittance. So absorbance equals to minus log of transmittance. If you just put the value of 25%, which is the 0.25, minus log of 0.25, it comes about zero point 0.6. Zero point 0.6 is the correct answer. Basically, the said that the absorbance is proportional to the concentration. So if absorbance and intensity are known, the concentration may be calculated by measuring the magnitude of the absorbance in the IR spectrum. However, it is not largely recommended to quantify based on the IR spectrum. So the infrared spectrophotometer instrumentation, we see it's shown an example of the FTIR Michelson interferometer. The spectrum is collected using an FTIR device using a device known as a interferometry. Here the interferometer is composed of the following components: a source, a beam splitter, moving mirror, and stationary mirror, and a detector. One half is sent to the moving mirror while the other half is reflected to the stationary mirror. The mirrors recombine the two beams at a beam splitter. The moving mirror's beam has gone a greater distance than the stationary mirror's beam. The beam splitter then sends the interferogram to the sample, where it absorbs some energy and transmits some. The detector receives the sent part. The interferogram is transformed to a spectrum using a computer technique called the Fourier transform. Transformation of the Fourier series convert an interferogram intensity versus the difference in optical parts to an infrared spectrum, where the intensity versus wave number is plotted. So Fourier transform is used to convert the data in the function of which domain to which domain, frequency and time respectively, time and frequency respectively, optical distance and frequency, or none of these. So the correct answer is time and frequency respectively. So Fourier transform is used to convert the data between a function in the time domain and its frequency domain counterpart. Because the optical path difference is calculated by multiplying time by the speed of a moving mirror, it may be regarded to be in the time domain. The wave number is in the frequency domain because it equals frequency divided by the speed of the light. So it changes from the time domain to frequency domain, the data. Which of the following components is not a part of Michelson interferometer? Fixed mirror, grating, moving mirror, beam splitter. So the correct answer is grating. So basically a Michelson interferometer has these particular parts: the detector, the stationary mirror or the fixed mirror, the moving mirror, and obviously beam splitter. It splits the infrared source beam to one part towards the moving mirror and one part towards the stationary mirror, and then it gets combined to the detector. Whereas the grating is particularly a part of the normal dispersive infrared spectroscopy technique. Okay. So it have this kind of parts where the sample is put here, and based on this particular lenses and also the grating, and finally through the slit it goes to the detector. Which of the following is not an advantage of operating an FTIR over IR? Improvement in signal to noise ratio. FTIR spectrophotometer, all frequencies are recorded simultaneously. Higher resolution, higher throughput. So the correct answer is FTIR spectrophotometer. All frequencies are recorded simultaneously. So FTIR having these advantages: higher throughput, which means an improvement in signal to noise ratio, the fail gates advantage, uh, and also the higher resolution. But in dispersive IR spectrophotometer, the intensity of the IR light at different frequencies are recorded sequentially, where the FTIR spectrophotometer, all the frequencies are recorded simultaneously. Okay, so the transmittance examination technology, one of the most commonly used examination method. The advantage includes the ability to produce excellent signal to noise ratio for the samples in any form, in the solid, liquid or gaseous phase. The disadvantage of the sample, what is the sample thickness restriction, is that the thick sample absorbs so much infrared light that the detection of the infrared transmission is difficult. So the sample thickness, there is a limit of the sample thickness. It should not be more than 20 micrometer. Okay. So the solid samples may be in the form of thin film or powder. Transmittance technique. For polymeric material, the thin film samples are required. So it should be prepared by casting polymer solutions onto the films, by pressing mechanically at higher temperatures, or the powder specimens can also be used, which can be prepared by grinding a solid sample in the presence of an infrared inert matrix material such as KBr or potassium bromide, amount weight of 350 mg. The mixture is transported to a die that is put in a press. So it produces a clear glassy disc approximately 1 millimeter thick under high pressure. This disc then will be available for transmission analysis. Transmission mittens technique with respect to gas and liquids. So there will be requirement of particular special cells or a certain thin film method. The ATR technique depends on the Snell's law, total internal reflection, evanescent wave, or all of this. So all of these basically are the correct answer. So the ATR technique depends on the Snell's law. It depends on the total internal reflection technique and also the evanescent wave. So from Snell's law, it comes is about n1 sine theta 1 equals to n2 sine theta 2. So if n1 is greater than n2, n is basically refractive index of the particular medium through which the particular ray is passing. So the angle of refraction is always higher than the 90 degrees. Uh, so and it obviously becomes a particular greater than a particular critical angle of the incidence, which is termed as theta c. So in this condition, no incoming light is transmitted and is entirely reflected back to medium 1, which is called as the total internal deflection. Okay. So from Snell's law, the critical angle theta c can be obtained by setting theta 2 equals to 90 degree. Okay. So if theta 2 becomes 90 degree like this, so what happens is theta 2 equals 90 degree. So sine theta 2 will be 1. We will be having the theta will be having the theta 1 is having the equal to the theta c. So this particular total internal reflection will occur when the radiation traveling from higher refractive index material to lower refractive index material and at the critical angle of reflectance. And the importance or the advantages of this particular ATRIR technique is there is no requirement of sample preparation and excellent repeatability of spectral values. And that is why in recent years, the attenuated total reflectance method, the ATRIR spectral method, having the uh, having the most advantages and having the revolutionary uh, method in the solid and liquid sample analysis. So the last spectroscopic technique which we are going to discuss is the Raman spectroscopy. The Raman spectroscopy technique is used to determine the interior structure of the molecules and crystals. It is based on the phenomenon of electromagnetic energy being scattered by molecules. Both elastic and inelastic scattering by molecules are possible. This is decided by the frequency of the dispersed light. Elastic scattering is also referred to as Rayleigh scattering, and the inelastic scattering is basically referred to as the Raman scattering. So basic the comparison between the infrared absorption and the Raman scattering. If you see the several frequencies of infrared region is directed onto the sample, whereas the sample is irradiated with the intense radiation of a particular single frequency in case of the Raman spectroscopy. Okay. The frequency of the incident radiation matches the energy difference between the ground and excited state of a vibration, absorption occurs, and the frequency is lost as a result of the incident radiation. Okay. On the other hand, what happens in the Raman spectroscopy is when light interacts with the sample, an unstable high energy virtual state. It is not an particular original state. It is kind of an hypothetical state is created because of the unstable high energy uh, molecule. The photon is re-radiated rapidly. So obviously it cannot stay at that particular virtual state for much longer time because of this uh, unstable nature. So the energy of the re-radiated photon is reduced by an amount equal to the difference of the energy between ground and excited state, and thus detected. And this is called the Raman shift. Okay, so the energy difference between this particular ground state and the amount of the energy of the photon which is released, that is actually the we see the particular uh, peak of this particular in this particular spectra. So to be IR active, a vibrational mode must induce changes in the dipole moment of a molecule in the infrared spectroscopy. Whereas for a Raman active mode, the vibrational mode must induce changes in the polarizability of a molecule. You must see what is the particular thing which is called as polarizability. This is your task for the next class. So there is a difference between this infrared spectroscopy and Raman spectroscopy. There is the dipole moment should be changed, whereas for Raman spectroscopy, it should be changed in the polarizability. So you should check the definition of this particular terminology. So infrared spectroscopy is used to determine the frequency of absorbed light, whereas the change of the frequencies of the scattered light is measured in the Raman spectroscopy. If it is the elastic scattering, so the same energy is transferred, but energy is lost by the incident molecule is the elastic scattering. Then it's called the Rayleigh scattering, and if it's the inelastic scattering, then it's called the Raman scattering. So the intensity of the scattered light is actually low. So whenever scattering happens, maybe a million scattering is happening when this particular phenomena is occurring in the spectroscopy. So among them, the million scattering, maybe 10 or 12 would be the inelastic scattering. So that is why it's called the intensity of the scattered light is actually low, and that is why we require an intense source and a very sensitive detector. And that is why Raman spectroscopy is actually called a very highly powerful technique, but also requires a very sensitive on a very delicate technique. That is why. So the symmetric vibrations produce the greatest change in polarizability and scatter the light in a higher extent in Raman spectroscopy. The infrared absorption is most severe when asymmetric vibrations produce a large shift in the dipole moment, already told for the infrared absorption. So that is in by these particular ways, the two techniques produce quite dissimilar patterns of intensity. Raman and infrared spectroscopy are frequently complementary and used in conjunction to provide a more detailed view of a molecule's vibrational structure. Okay, in some cases, the molecule's vibration can possess both infrared and Raman active. So, our rule of thumb basically symmetric is Raman active, asymmetric is IR active. Okay, because with the help of the symmetry, it does not mean that the dipole moment change will be not it will be equal to zero, but it does not mean the change in the polarizability will be equal to zero. That is why the Raman spectroscopy is this particular molecule it's called as a it's Raman active. That is why you see that the graphite maybe or the carbonaceous materials, carbon carbon single bond, carbon carbon double bond, we characterize it by the Raman spectroscopy. it gives a particular band, but you cannot get enough peak via the IR spectroscopy or the FTIR spectroscopy due to this reason. Okay, because this is not the IR active, because this net dipole moment change is zero, whereas its net polarizability change is not zero, and that is why it's Raman active, and gives us peaks in certain locations. So the laser used for generating an intense Raman shift is made of these are the four options: Nd:YAG, ruby laser, helium neon laser, argon or krypton laser. So the correct answer is the argon or krypton laser, because the source of the laser from argon and krypton are the most intense. So if you see, there is a different frequency values are given for the different laser sources: the argon, krypton, helium or neon, diode laser, or ND or YAG. So the argon and krypton having the highest frequency or the highest wave number. And as I told earlier, the laser source should be highly intense for this particular technique to be performed, for Raman spectroscopy to be performed. The low frequency lasers, the diode laser and ND/YAG laser minimizes the interfering fluorescence spectral lights. An easiest way to mask fluorescence in Raman spectroscopy is to use the longer or near infrared wavelength excitation laser, using pulsed laser source, use continuous wavelength, or both use of longer or near infrared wavelength excitation laser and using pulsed laser source. So the correct answer is to use both the use of longer or near infrared wavelength excitation laser and pulsed laser source. Okay, so fluorescence is basically the samples or impurities which may absorb laser radiation and re-emit, uh, uh, which emit as a fluorescence. In fluorescence, the incident light is completely absorbed and the system is raised to higher vibrational energy state, from which it can go to various lower energy states only after a certain lifetime. As a result, what happens is a photon with a different frequency than the incoming photon is generated, and the molecule is ultimately at a higher or lower energy level than it was at the original state. So basically, the original data which we wanted to retrieve, we are not obtaining that. We are obtaining some other data. So in the visible region of the spectrum, fluorescence is more observed, and fluorescence may totally obscure the Raman spectrum, and this is a major drawback of using the Raman spectroscopy. So basically, how we can mask this particular fluorescence, and use a longer or near infrared wavelength excitation laser. Okay, so the energy supplied is less, and so will be the virtual states. So this is the kind of a trade-off. So we give more and more energy, which means that we are going towards the uh, visible region, which means that the higher energy supplied, it can have a higher chances of the fluorescence. As a result, the likelihood of the virtual state overlapping an upper electronic state is reduced. So given very high energy, so your excited uh, electron or photon, basically it does not reside at the virtual or the hypothetical state, but it gets more excited, and it goes eventually to a upper electronic state. Okay, so and by that way the fluorescence happens. So the longer or near infrared wavelength excitation laser, it can mask, or a pulsed laser source in a pulsed manner, that the because of the lifetime of the Raman scattering is much shorter than the fluorescence. A pulsed laser source may be used to differentiate between the Raman and fluorescence utilizing the time gap. So not in a continuous manner, but in a pulsed manner. If we give the laser to this particular sample, we can also mask the fluorescence in Raman spectroscopy. So that is all from my side. Thank you for joining, and if anything you need to discuss, you can discuss, or otherwise we'll stop today's meeting.
Hello, sir. One request. Hello.
Yeah.
One request, sir. If you give a PDF format of the PowerPoint, means it will be easy to read, because every time we have to go and see the videos in a online only. We cannot able to download it, and we can see in a, when leisure time. If we that time we cannot able to operate the online mode. That's the problem. So only we can able to watch your videos in online only. No, that's somewhat difficult for us. So every time the data will be consuming. So if you give a permission to download, then we can download it, and we can watch anytime. No, that
So
problem we are facing. Or otherwise
so
you can give a PDF.
the PowerPoint you are talking about?
Yeah, PPT,
Yeah.
PowerPoint, PDF. If are available, means we are having easy
So
to download it, and whenever the time permits, we'll read it. So every time
so
listening the video is not at all possible. No.
yeah, I understand. So you are
Uh,
not able to retrieve that Google Drive link.
no, I can retrieve, but every time the data is consuming. No, if every time
So
I go and
from that
watch it.
you are not able to download.
I cannot able to download.
Okay, I'll check. Okay,
Ah,
okay,
yeah.
I'll check, and if not, I'll then try to upload the PPT here only so that you can
Yeah.
download and
If it
yeah.
so means I can refer, because I am working as a lecturer. So I'm
Mhm.
not having time while traveling. I can read it. If PDF is available, means I can read it. That's the problem. So when I am attending the meeting itself, I was in travel. Now only I reached home. No, so that time it is difficult to
Yeah,
hear.
I understand. I
Yeah, that's
understand.
a problem.
Yeah. Also,
If
also,
possible, if you post it,
yeah.
it could
Okay.
be better for learning.
Okay. Thank you for your concern. I'll check and I'll do the needful.
Yeah, thank you.
Thank
Thank you very much.